Welcome to the presentation on the road weather forecasting. This presentation is prepared by the Finnish Meteorological Institute as part of the Green Intertraffic project, funded by the European Union, the Russian Federation, and the Republic of Finland. This presentation will give the information about what the road weather means, meteorological observations on the roads, the methods to predict road weather conditions, in particular, about the road weather model, and also about the influence of local factors on the weather conditions of the road surface. When we talk about road weather, we mean weather-dependent driving conditions. The components of the road weather are visibility, precipitation, wind speed and wind direction, air temperature and road surface temperature, water, ice, and snow content on the road surface. The most important factors affecting driving conditions are visibility and slipperiness. Visibility can be affected by fog, rain, or snow that is falling or carried by the wind. Slipperiness depends on the amount and composition of water, ice, and snow on the road surface. Why predicting road weather is important? Accurate forecasts can be used to anticipate road freezing, so that roads can be salted before ice starts to form. That will make roads safer for drivers. In addition, accurate forecasts enable financial savings, as unnecessary salting can be avoided, in case when the road temperature is not actually going to be below 0 degrees. Road weather is observed in Finland mainly by using road weather stations and road weather cameras. There are about 400 road weather stations in Finland, which are typically located at the side of the road. The picture shows Vaisalas road weather station, which is equipped with a wind measuring instrument, optical instrument measuring friction and surface temperature, a visibility meter, thermometer, humidity meter, a rain gauge, and an asphalt-mounted temperature sensor. Both road weather station observations and images from road weather cameras can be viewed on the website of the Traffic Management Finland given here. In addition to road weather stations and weather cameras, observations are now also available from cars, although not yet to any significant extent. For example, modern cars already measure air temperature, and the use of windshield wipers could provide more information about where it's raining. The picture shows a pair of tachometer devices attached to the back of the car to measure road condition, friction, and road surface temperature. The basis for nowadays weather forecasts are numerical weather prediction models running on supercomputers. These models describe the basic physical and dynamic processes behind the major weather phenomena. This animation shows simulation results for a period of 54 hours. This essentially is a forecast. The input to these models are meteorological observations data, which are regularly received from a global network of synoptic stations, meteorological soundings, satellites, aircrafts and ships, buoys, meteorological radars, and other sources. Before publishing, the simulation results are edited by a meteorologist. Typically, meteorological services use the results of several models running at national and international meteorological centers, and, based on the experience, the meteorologist picks more appropriate forecast and, if needed, makes corrections to it. The predicted quantities are then used in the road weather model to predict meteorological conditions of the road surface. The road weather forecast itself is made using a specific road weather model developed. This presentation will talk about the road weather model developed by the Finnish Meteorological Institute. However, several other models have the same operating principle. For example, the so-called thermal road model, developed by the Institute of Radar Meteorology, St. Petersburg, Russia. The road weather model of the Finnish Meteorological Institute is a one-dimensional surface heat and moisture balance model. Since the interaction is simulated only in vertical, it is called one-dimensional. The balance of heat and moisture at the surface is determined by the difference in the total influx and outflow of heat and moisture due to such processes as solar and thermal radiation, air mixing, including mixing, which is caused by traffic, evaporation and condensation, precipitation, heat exchange in a layer of asphalt and ground. The input data to the road weather model are air temperature and humidity, wind speed, precipitation, data on radiation or cloudiness. These data are used to calculate the heat and moisture exchange between the atmosphere and the surface. A layer of asphalt and ground are divided into sublayers, between which heat transfer is modeled. The main result of the model is the temperature and water content in its various states on the road surface. How the simulation is done? The simulation consists of two phases, the initialization phase and the focus phase. In the initialization phase, the focus is made for a period of 48 hours preceding the current time. In the beginning of the model simulations, in this phase, the temperature of the top 4 layers is set to air or road surface temperature, and the temperature of the remaining layers decreases linearly with depth towards the climatology-dependent value of the bottom layer. In the initialization phase, meteorological observations are used as input to the road weather model. This is done to obtain more realistic temperature profiles at the current time. This profile is then used as the initial profile for the subsequent forecast. In the forecast phase, the input data to the road weather model are the results of a 3-dimensional weather prediction model, which were previously edited by a meteorologist. The results of the road weather model simulations are the prognostic values of the following quantities: road surface temperature, the amount of water, snow, and ice on the surface, friction coefficient of the road surface. These values are summarized in categories that describe meteorological condition of the road surface, such as dry, sleet, snow, and others. The model also generalizes the predicted values into the so-called traffic index, which describes driving condition and can have values: normal, difficult, very difficult. The model doesn't take into account all local factors, although their influence on the surface temperature and moisture can be large. For example, during the day, a stretch of road in the shade can be significantly colder than a surface that is exposed to the sun. In the opposite, at night, a road in the forest can be much warmer than one under the open sky. The road weather model assumes that the road is open, which can cause some errors. It would be possible to set sky view factor in the model, which describes how much of the sky is visible at the road point. However, such coefficients are not currently used because they are not readily available in Finland. Another example of local factors that have a significant impact on the meteorological condition of the road surface is the location of the road stretch near water. So, bridges passing over the water surface are more prone to icing. Also, surface height variability can lead to the formation of local circulation. This happens, for example, when the cooled and denser air goes down, pushing out warmer air. From all above, one can say that road weather forecasts play an important role in the road safety, as well as in reducing financial costs associated with the road maintenance. In turn, the accuracy of the forecast depends on the size of meteorological observations network and the accuracy of prognostic models. The more detailed physical processes are described by the models, the more accurate the forecast is. Weather observations also play an important role in tuning the model results on a specific road stretch. Data from cars can significantly expand the observations network, thus providing more detailed information both for weather prediction models and society. The talk was prepared by Virvi Karsisto and Evgeny Atlaskin, Finnish Meteorological Institute.